Hello, everybody, and welcome to the week 2 video for Math 4400. So just a couple of reminders. Your second homework is due Monday at 11:59 p.m. You'll have a quiz on this video due Tuesday at 8:30 a.m. And then, well, that's sort of standard for every week. The big reminder is, if possible, please bring a laptop or tablet to class next week. So I'll also send an announcement about this at the start of next week. And as I mentioned in class on Thursday, next week we're going to be doing mostly computations on a computer using this sort of Sage Math cell that I showed you. There'll be a worksheet with a lot of problems using that. Technically, and you can probably get it working on your phone, but it will be a lot slower to enter things in. So you'll be better off if you have a laptop or tablet to do that with. And you can access the Sage Math cell. There's a link at the top of the Canvas page, so you can try it out on whatever you're planning to bring. Of course, you can always work with someone else in class who has a laptop if you aren't able to bring one or a tablet, but it'll be better. The more people that have them, the better. So thanks for that. Okay, good. So what were the key takeaways from week 2 in this class? Well, maybe one big takeaway is, if you didn't believe this already, you saw that sort of linear algebra is a really powerful tool. Linear algebra has lots of results and structure that we can use to justify interesting statements. So we saw that this week when we sort of were using dot products to sort of understand linear independence, and then by linear independence sort of told us something about the number of clubs we could have under different rules, like club town and even town and odd town. So linear algebra is a powerful tool, and sort of going back to this basic idea that we're going to see again and again in number theory. When you have simple questions, you often need to rephrase them in sort of some other way where you can introduce more structure. So this club town stuff, we rephrase these questions about clubs in terms of questions about their membership vectors. And that rephrasing let us use tools from linear algebra to understand them. And that sort of gave us some powerful options for how we approached things. Okay, and so what are some other things? Well, another big thing we learned about that we'll be using a lot more as the class goes on is this notion of a field. So something that behaves like the rational numbers, the real numbers, or the complex numbers, where you can sort of add, subtract, multiply, and divide by non-zero numbers. In particular, we saw sort of the field with 2 elements was sort of really useful, for this odd town and even town stuff. And then more generally, we sort of started talking about other finite fields, like the field with p elements. So F2 is a field with 2 elements. Fp was a field with p elements, where p is a prime. And then, good, and sort of building on that, we sort of talked a lot about isotropic vectors. Sort of if you look at this optional exercise at the end, you'll see sort of how that connects everything to even town. We talked about square roots of -1 in finite fields, and that's sort of a theme we'll be coming back to later on. So we saw sort of some interesting things already using finite fields. Okay, so, well, what I want to do in this video is just talk a little bit about a connection between some of this club stuff, which sort of just sounds like, basically these are fun problems, but it's not clear that it's actually useful or interesting or for anything. But there's actually sort of an interesting connection between these club problems, and in particular even town, to something called coding theory. That actually is a very important subject, for example, in how computers function. So I want to say a bit about that. And so to start, I should, and this is essentially an optional topic. We're not going to do too much more with it, but I just want to mention it and sort of mention how it connects. So you see that sort of we really are doing interesting things here. It's not sort of just not interesting just sort of from a fun perspective, because it's fun to play with Club Town. It's sort of interesting also from an applied perspective. Okay, so right, what is coding theory? Well, let me just remind you how a computer stores information. I mean, a computer stores information as sort of just a list of zeros and ones. So each bit is a bit is a 0 or a 1. So a bit is one piece of information, and okay. You can sort of combine those together to sort of encode more information. So a byte is sort of 8 bits. So you have 8 zeros or ones in a row. And if you have 8 bits, well, we have something called the ASCII character code, so ASCII, which sort of assigns to each sort of to each byte, so each string of 8 zeros and ones, 8 zeros or ones, a character. So the character capital A corresponds to 0, 1, 0, 0, 0, 0, 0, 1. The ampersand character corresponds to 001001110. And so when you're typing, like if I type a capital A, like this is what gets stored actually in your computer to remember that you sort of type a capital A, or that maybe like this is what gets transmitted from your keyboard to your computer to tell it that sort of you type a capital A. Okay, well, actually there are other character codes now, but sort of at least originally this was definitely what was being used. Okay, and so, well, that's how computers work, but like we've seen strings of zeros and ones a lot recently. We know like if I have 8 zeros and ones in a row, like if I have a byte, well, I could also think of that as just a vector in f2 to the 8. So in f2 to the 8, like Rn. So column vectors with 8 entries in f2. Okay, so well, we know how many vectors are in this. So here's a little exercise. I'll put this in the video quiz. If each byte encodes an ASCII character, how many ASCII characters are there? Well, I'm just asking sort of how many vectors are there in f2 to the 8 when I ask that question. Okay, good. So that's how computers encode information, sort of using bits and bytes, so strings of zeros and ones. And so when a computer functions, like whether it's sort of functioning by itself or like functioning like interacting with other computers like on the internet, I mean, it has to transmit information. It's like you have to transmit information from like your keyboard to the CPU. You have to transmit information like, I mean, like modern computers have like 8 different CPUs, and so they have to transmit information between those different processing units. If you're sort of sending information to the internet, you have to sort of transmit information from your computer to another computer. And when you do that, and you're just sending out like a strings of zeros or ones, like using sort of electrical signals. But there's a problem with that, which is transmission is unreliable. I mean, if you have sort of like an electric current like running through a wire, like that can sort of like bits can get flipped. Like you can sort of, some of those zeros can get turned into ones and vice versa, just by sort of electrical interference. Maybe there's like some other electronics nearby, there's not good shielding on the wire, and or just like no matter how good of shielding you put on things, like there's always some electrical noise, electrical interference, and you can really like you can send one thing and sort of like from one CPU, and then like the other CPU receives a different thing, like a bit got flipped. Okay, so like we need, for a computer to function, like we need to be able to wrestle with that. We need to be able to like tell when we got the wrong thing. We need to be able to tell somebody when there was an error in the transmission. Okay, and so error correcting codes are basically about like how we can do that, how we can sort of detect when sort of some bit has been flipped. So here's like a really basic thing you could do. Instead of sort of just sending each byte of information once, you could just send each byte twice. So that's called a repeating code. You just send your 8 zeros and ones, and then you send the same 8 zeros and ones. So when sort of the receiving, the recipient gets that, they can look and like they can check, okay, did I get the same thing twice? Okay, then probably there weren't any errors. I mean, sort of concretely, this can, like, if this is a good system, like if you know that you're going to, like, every time you send 16 bits, you're going to make at most 1 error. Somehow, if it was possible, you could make 2 errors, like get 2 bits flipped, then you could sort of flip the same one and both repeating, and like that would be some error that wasn't detected. So morally speaking, like this system where you sort of send each byte twice, that can detect as long as you know detect errors, as long as you know like there's at most 1 error being made per 2 bytes. Somehow it can be broken if there's possibility of more than 1 error in 2 bytes. Good. So that's but okay. So if you have some estimate about how reliable your system is, then this could be used. I want to point out one nice thing about this code is that if you think about it, like this is giving you a linear transformation from f2 to the 8. So this is sort of your byte of information, and then it's encoding it as 2 bytes in f2 to 16. But sort of this map from f2 to the 8 to f2 to 16. This is a linear transformation. So it's not just sort of an arbitrary function, it's sort of a linear transformation. And one nice thing about that is it makes sort of encoding and decoding and sort of doing computations with this very quick, because sort of linear algebra is something we can do quickly on a computer. So it's nice when sort of our error, sort of our codes are error correcting codes. It's nice when they sort of are given by linear maps. And so that's something you sort of want in a theory of error correcting codes oftentimes. Okay, so that's sort of one basic example. I mean, that's actually a pretty bad code. Like we have to sort of transmit twice as much information, 16 bits instead of 8 bits, in order to detect just a single error. And so that's not great. And so you might ask, like, can we do better? Like, are there more efficient ways of detecting errors? And so one sort of standard example takes a byte and sort of then adds just a single bit to it. So this is called a parity bit. And what I do is I take a vector. So I take sort of my eight zeros and ones and make them bytes, like for example, this one. And okay, I sort of give myself a new vector where I sort of just take that vector there. And then I add one more entry to it. So I'm going to start taking 8 bits and I'll output 9 bits. Well, if I have an even number of ones in my 8 bits, I'm going to put a 0 here. And if I have an odd number, I'll put a 1 in this sort of last entry I added. So that first one goes to, I added a 0 at the end. And then this next example has an odd number of ones in it. So I add a 1 at the end. So this sort of takes in 8 bits and sort of outputs 9 bits. Actually, if you sort of think about this, you'll see this is given by a matrix. This is also a linear transformation. It's given by this matrix. And somehow the point is sort of if I want to detect whether like the number of the number of entries of a 1 is even or odd, I can just add up all those entries sort of in F2. I'll get a 0 if it's even and a 1 if it's odd. So that's sort of why we have this last row down here for this encoding. And actually, this can detect if you know there's at most one error sort of per 9 bits, then this will detect that error. And why? I mean, somehow like basically if you change one of the first 8 bits, like that will change whether the number is even or odd. So you'll see like if you change one of these, then you'd sort of like if I change this one to a 1, then now I'd have an odd number of ones, but I have this 0 down here telling me I should have an even number of ones. So I'd be able to detect that. And if I change this last one, like I'd still have an even number of ones, but now this would be telling me I should have an odd number of ones. So adding this parity bit, you can detect as long as you know, you can detect errors as long as you know there's going to be at most one that happens. Let me point out in both of these codes, like the parity bit and the repeating code, you can detect sort of when you know there's at most one error, but you don't know how to fix it. Like in this repeating code, okay, like you can see where the error is, but you don't know like whether the first transmission, like the first 8 bytes or like 8 bits or the second 8 bits was the right one. So you sort of see an error was made, but you don't know which one, which one is right. So you can't fix the error. Here in this parity bit, like again, sort of you know an error was made, but you don't know which bit was changed. So like when you detect this error, you just have to ask the other computer to resend the byte, to resend the message. Okay, good. But well, this parity bit though, this is much more efficient than the repeating code because to like encode, I only have to do 9 bits to send 8 bits of information while detecting that sort of one error. So that's pretty good. But it's sort of interesting to look for sort of even more robust codes than that and sort of think about how you can sort of produce nice codes. And it turns out you can sort of give some like very effective codes and do sort of very interesting things. One example is called the Hamming code. So this is sort of set up a little bit differently. And you sort of break up, instead of doing a byte, you should sort of break up your information into sort of 4 bits at a time. So you break up a byte into sort of 2 bits, 2 sets of 4 bits. And so the Hamming code sort of takes sort of 4 bits and sort of outputs 8 bits. So like the repeating code, it sort of doubles the length. So okay, that's not so good. But unlike the repeating code, it can sort of detect much more. So this can detect up to 3, like if you know you're going to make sort of up to 3 errors every time you transmit 8 bits, then this can detect it. I mean, that's pretty good. I mean, that's like, up to 3 errors, that's like, you're transmitting 8 bits, if you're allowed to make 3 errors, that's like almost half the information that you're sending could be wrong, and you'd be able to detect that. So this is sort of good, like if you have a very noisy transmission line where it's subject to like lots of errors. You can sort of detect up to 3 errors, and actually you can sort of even fix one of them. Like if you know there's at most 1 error that's gonna be made, this will let you fix it when it's made. without sort of have to resend information. Like somehow this Hamming code will give you enough information to do it. And it's also linear, so it's sort of encoded by an 8x4 matrix that gives a linear transformation. And the connection sort of everything we're doing is, we've done sort of this last week, is actually if you look at this matrix and you look at the column space, so the subspace spanned by the subspace spanned by the columns. So this is some in F2 to 8. Well, this is something called a maximal totally isotropic subspace. This is sort of related to the notion of isotropic vectors, but sort of generalizing a little bit to subspaces. I mean, somehow if you do this sort of optional exercise, 2. Sorry, not 2.6, this is wrong. This is 3.6. This optional exercise 3.6 on the week 2 worksheet, then what you'll see is sort of a maximal totally isotropic subspace is actually the same as a maximal system of clubs in Eventown. So this Eventown problem we're talking about sort of was about sort of finding these maximal totally isotropic subspaces in hiding. And while like somehow these maximal totally isotropic subspaces actually have something to do with like finding efficient error correcting codes. If you want to understand this connection, you can sort of work through that exercise 3.6 on the week 2 worksheet. And then there's going to be sort of more optional stuff on the week 3 worksheet, sort of describing a little bit more about this Hamming code, what it is, and sort of why it can sort of have these properties. Okay, so that's all I wanted to say today. Have a good weekend.